So our next speaker is going to be Ping Hu, and he's going to talk about revisiting risk-sensitive MDPs, new algorithms, and results.
Okay, finally, my presentation is not about Monte Carlo and sampling. Hi, everyone. My name is Ping Hu. Today, my presentation is about revisiting risk-sensitive MDP, and we provide a new algorithm and result. This work is done with Yeoh, who is my advisor over there. We're both in New Mexico State University, and Pradeep, who is in Singapore Management University. Okay, for some planning task, the agent only have limited resource. For example, for the mass over, they may only have limited power or limited storage. Under this kind of situation, of course, the agent want to achieve the goal, but they want to avoid to use up their resource. So this is the motivation for this work. Okay, this is the formal definition about MDPs. It includes a set of state, an initial state, and a subset state as goal, and a set of action and transition and cost function, which is the transition probability and cost value. When an agent starts from IS, apply action, and go to a successor state. Original or traditional solver MDP means you need to find a policy which is mapping from state to action to minimize the accumulated expected cost. But what if the agent really want to avoid the accumulated cost? For the above situation, the agent will want to avoid the situation that use up their resource. We use a small example to illustrate this. This is a small example. We assume the initial state is S0 and all other 4 states are goal state. If you measure the expected cost, then for action A1, it's the sum for both branch. 3 plus 14 is 17, and for action 2, it's 16. So now A2 is better because it has smaller expected cost. But let's see if the agent have only limited resource. For example, let's see the agent have limited resource as 14. We call it the cost threshold. Then if they want to maximum the probability to achieving the goal, to accomplish the goal, we call it a reachable probability. Then the situation is changed. Now for A1, only the first branch, the costs are smaller than the threshold. So for action 1, they can reach the state with probability 0.3. But for A2, for both branches, the costs are actually bigger than the threshold. So for action A2, the reachable probability is 0. So now action A1 is better. The interesting thing is, let's assume the agent have different amount of resource. For example, 16. Then the situation change again. Now for A1, the probability is still 0.3, but for A2, for this branch, the costs are smaller than the resource. Then the reachable probability is 0.8. So now A2 is better again. So let's come back to the motivation problem. If the agent only have limited resource, it's same as they have a utility function like this. For example, let's see the mass over. They only have power as theta 0. That means if the accumulated costs are less than theta 0, they get a specific utility because they accomplish the goal. Otherwise, if the accumulated costs are bigger than theta 0, then they get no probability. So for this kind of situation, a more reasonable criteria should be the agent need to maximum the probability to achieving the goal, but with the accumulated cost less than the resource it holds. Okay, this is a formal definition about risk-sensitive MDP. It includes the original MDP and a set of possible cost threshold, and theta 0 is the initial cost threshold. Initially the agent holds the resource like this. Instead of the original policy, which is a mapping start from state to action, now for this kind of situation, because we show in the above example, the choice for the agent not only depend on the state, but also depend on how much resource they hold. So also depend on the cost threshold. So risk-sensitive MDP policy should be the mapping from the pair of the original state and the cost threshold to the action. We call the pair of original state and cost threshold as the augmented state here. So solving a risk-sensitive MDP means you need to find this kind of policy which maximally reachable probability. Here, for some planning tasks such as mass over, they may have more than one kind of cost or and the constraint. For example, mass over has limited power and limited storage. So our model can naturally be extended to handle this kind of situation. You just add a new cost and threshold. Okay, similar to BM update, we provide the solution update to calculate the reachable probability. You could see the reachable probability for the augmented state have 3 cases. The first case is for the next transition, if the costs are bigger than the threshold, that means the agent will use up their resource, then the reachable probability are 0. Otherwise, if the successor state is a goal, then they can reach the goal safely, of course. And the reachable probability is the transition probability. Otherwise, if the successor is not a goal, the reachable probability can be recursively defined as the transition probability times the reachable probability of the successor state. Okay, you could see actually this update defines a transition relationship between the augmented state. So based on that, we can build an augmented MDP. Here, this is an original MDP example. We assume S0 is the initial state and S4 is the goal state. Let's see if the agent hold resource as 6 at the beginning, then we can get a transition relationship like this. And for example, here, let's see the agent start from 0 and go to S0 and go to S1, and the cost is 2, so the cost threshold reduce from 6 to 4. Here, if we want to calculate the reachable probability, we can assume this MDP associated with a specific kind of reward. That means for all states which is goal and with no negative cost threshold, we assume it's goal. So the transition here associated with the reward 1. That means 100%. Otherwise, for all other edge and transition, the reward is just 0. Then you don't get it. There are 2 important properties about risk-sensitive MDP. The first one is solving a risk-sensitive MDP is p-hard in the original state space. This is because a circuit value problem can be reduced to this problem. And the second thing is for RS-MDP, the optimal policy is stationary and deterministic in the augmented state space. Because the agent only needs to know how much resource I still hold. That means the cost threshold already contain all the important information about the history. Okay, now we start to introduce our argument. We all know for MDP, we can analyze and divide the state space to different strongly connected components. We call it SCC, and they will form a SCC tree. And normally they call it directed cyclic graph, DIJ. For the augmented state space, we can divide it to different SCC like this. There are something interesting for this structure. The first thing is because we don't allow negative cycle. Of course, if there are negative cycle, the agent will stay there forever. So all the cycle inside one SCC must only encounter the accumulated cost is 0. The second thing is, if there are no negative costs, then all the augmented state inside one SCC must have exactly same amount of cost threshold. Okay, now we introduce our first algorithm is TVI DFS. We call it TVI because it is essentially the same as applying topology value iteration, which is another algorithm for MDP to the augmented state space. I want to show the process to calculate it. At the beginning, for all the NIF state with negative cost threshold, of course, the reachable probability are 0. Then, based on the updated equation, you can calculate the reachable probability for this branch. It's also 0. And for the goal state with no negative cost threshold, the reachable probability is 1. And now you can calculate this as 1. Then you can calculate the reachable probability for the state in the SCC and get a number like this. Finally, you get the reachable probability of the initial state. So this is actually the same as you apply a depth first search on the SCC tree on the DIJ, and you can even use some branch and bound strategy to cut some branch. And if you only allow positive cost, then all the SCC will reduce to just one single augmented state. Then the algorithm will be DFS directly. By applying this algorithm, finally you will get the reachable probability for the augmented state in the SCC tree as the table shows. Here you might notice, let's say for two augmented states with same original state and the cost threshold is very close, they might have exactly same reachable probability. So based on this observation, we have the second algorithm. We call it TIDP, and DP means dynamic programming. The power aspect of TIDP is they can solve a risk-sensitive MDP for multiple cost thresholds in just one swap. There are two things different between TIDFS and TIDP is TIDFS extend the SCC tree start from the initial state, but TIDP extend the SCC tree from the goal state. You could see here, actually the number is different. And the second difference is for all the augmented states which is not in the SCC tree, they will have exactly same reachable probability as the augmented state with same original state, but with smaller cost threshold. So finally, you can get the full table of the reachable probability. Then this is good for situation like, let's say, sometimes you don't know the cost threshold at the beginning, I mean in advance. Or you want to solve a risk-sensitive MDP for multiple possible cost threshold, then TIDP is a better choice. Okay, in the experiment, we compare our algorithm with two existing algorithms. The first one is provided by Yeoh. They don't name it, but it is essentially the same as apply value iteration on the augmented state space. The second one is a functional value iteration. It is designed for a more general utility function. And we compare our algorithm on two sets of domains. The first set, we just randomly generate some MDP. The second set is the IPPC domain. This is the result for the random generated MDP. The x coordinate is the cost threshold, different level of cost threshold, and the y coordinate is the processing time. And here, the black one is VI, red one is FVI, and the green one is TIDFS, and the blue one is TIDP. The scale is exponential, so you could see TIDFS and TIDP are much faster than VI and FVI. For this set of instances, we only assume one goal state. So TIDP is faster than TIDFS. Here, this is a result for different set of instances with different number of ghost state. The x-coordinate is the number of ghost state, and the y-coordinate is the processing time. You could see at the beginning, when the number of ghost states are small, TI-DP is faster. This is because TI-DP have smaller processing time on each SCC. When the number of ghost states become larger, then TI-DFS become faster. This is because TI-DP extends the SCC tree from the ghost state. So if there are more ghost states, finally TI-DP will cover the whole augmented state space. And here, the interesting thing is you could see actually VI and TI-DP can, VI and TI-DFS can only solve one cost threshold, and the TI-DP and the FVI can solve it for all. This is the result for IPPC domain. The y-coordinate is processing time. You could see for all 8 domains, the TI-DFS is the fastest one. And this result is constant because for IPPC instance, they are all finite horizon problem. For finite horizon problem, all the states in the last horizon are the ghost states. So the number of ghost states are kind of big. That's why TI-DFS is the fastest one. Okay, finally, the conclusion about this work. In this work, we revisit the risk-sensitive MDP, and actually we give a formal definition about this problem. We introduced 2 algorithms, TI-DFS and TI-DP, and in the experiment we show TI-DFS and TI-DP are much faster than both VI and FVI. Okay, thank you. Oh, okay, here, I want to thank you some people face-to-face. I want to thank Andrew, Bly, and Scott, because for this work, they help us a lot. Andrew provided the first model about reachable probability, and he helped us to prove the hardness of this problem. And Bryce's suggestion actually need me to think about this risk control issue. And Scott provided IPPC domain, and he explained some detail about the instance to me. Thank you.
Hello?
Question. Yeah. Okay, so yes, I was just wondering, is there a form of proof that the optimal policies are deterministic and non-positive?
Group, you mean?
Is there a form of proof?
Yeah, we have the proof. Yeah, exactly. So it's stationary and deterministic in the augmented state space, but not in the original state space, of course.
Oh, sure, but yeah.
Yeah, we have the formal proof, but it's not in the paper, because the paper is short. If you want the formal proof, I can send you, or we can talk after this. We have both proof for the hardness and the determinist. The policy, the optimal policy is deterministic and stationary.
So Hector, do you have a question?
No, I try not to be in the middle of the thing, but I am, I know.
No, closer look. Any other questions?
Yeah. So is your cost, is it finite domain?
It's for all kind of domain. It can be, no. Let me give a specific. Okay, for all 3 kind of domain, let's say finite horizon and shortest parse, the stochastic shortest parse, and for the discount factor infinite horizon.
I mean your theta that you had there.
Oh, the experiment have, we have 2 sets, is that right? For IPPC domain, it's finite horizon because IPPC domain is. And for the first set, it's the shortest, it's a stochastic shortest parse problem.
So let's thank the speaker again. You could ask questions.